a break.
I'm going to talk on ternary logic and computer design. And the first thing I wanted to talk about is my motivation for doing this. And basically, several years ago, I learned about ternary logic as a potential alternative to binary logic. And theoretically, ternary logic is a more efficient way to represent numbers. And the idea is that the best ratio between symbols and the expansion of a number turns out to be base e. But that in some ways it's kind of awkward because 3 would look something like e to like 2 plus then e to some power plus e to a smaller power and so forth. So I don't recall the just a second. Guys, you need to be quiet now. I'm giving a presentation. So I don't recall the actual expansion, but basically it's something rather awkward for integers. But apparently if you're doing that allows you to use the least number of symbols for whatever expansion of numbers you wanted. And basically, if you rounded e to the next integer, you'd get to 3. And since it's kind of natural in electronic circuits to talk about negative, positive, and zero voltage, it would seem to make a natural fit for computers as well. And so I wanted to explore this, and so I wanted to first of all, I wanted to see what ternary circuits would look like. And I also wanted to, since there's a potential for being better than binary, I wanted to understand how those kinds of circuits might be optimized. And I also have a grand impossible desire where I would like to actually create a silicon computer. And it'd be kind of interesting if I could do that in ternary. And one of the reasons why I consider that an impossible desire, though, is because it's my understanding that it can be actually rather expensive to make it to etch silicon. And so I wanted to focus on the electronics of designing a computer circuit of some sort. I wanted to contrast this with another project that I find really fascinating, and that's actually more of a computer class called NAND to Tetris in 12 steps. And the purpose of the project, which is one of the reasons why I'm mentioning this, is because there's also a goal to design a computer. And the focus is to go from gates to build up to an operating system and a computer language and then an application. And in this case, since the goal is to provide an overall understanding of how all the little bits of computers fit together from beginning to application, everything is and to try to fit it in a single semester class, everything is simulated, and the system ignores some of the details like developing flip-flops or the system clock, and it also avoids optimizations. You could, if you're not careful with optimizations, you could get bogged down in any one of the steps. And I have some interesting results from looking at this. First of all, I learned how to design a computer. In some ways, that was kind of a quasi-goal, but I reached a certain point, which I'll be pointing out in the presentation, where when I put together a certain circuit, I realized that I kind of knew everything I would need in order to design a computer. And ironically, I still don't. At this point, I still don't know what working ternary circuits would look like. I have some ideas of what the circuits would look like, but so far my attempts have only released the magic smoke from transistors, and so they no longer work. I discovered some interesting design techniques for both computers and electronics in general, and I also learned that pretty much anyone can do these kinds of things. it takes a bit of effort, but it's not really beyond the reach of someone who puts their mind to doing it. And in this particular presentation, I'm actually going to be focusing more on circuits and on designing a computer. When I was at OpenWest, I gave a presentation that discussed the actual building of a computer, and in there I discussed different types of circuit logic and discussed techniques for putting circuits together. And actually, in that presentation, I also pointed out a computer called. I tried to show as many computers that people have built on their own for the different types of circuit logic, and for tube logic, I actually showed the picture of a computer called the Saturn, which was built in Moscow during the 1960s. And since it was a tube computer, it wasn't really an individual project, but it was a computer that ran on ternary logic. And interestingly enough, tube logic in general doesn't use binary. Instead, they tended to use base 10 logic. And one of the reasons why they did that was they wanted to try to reduce the circuitry as much as possible, so that they wouldn't have it to use so many tubes, and so that when tubes burned out, it wouldn't be as much of a disaster. And actually, come to think of it, one of the potential problems with ternary circuits that I've come to understand is that tube logic, or rather, that binary circuits aren't as susceptible to electrical noise, and I'm suspecting that the reason why tube logic was able to go up as high as base 10 was that it's when you have something like 400 volts going through the circuit, it's easier to make gradients between the voltages. Whereas if you're only working with 5 volts or 12 volts, or even as little as 3 volts, like modern day CMOS circuits, it's not as easy to differentiate between different levels of voltage. So first, I'm going to go over and review binary logic. And as I was preparing this, it occurred to me that I have an expectation that everyone would be familiar with it, but as I thought about it more, I realized that most of my binary logic exposure has mostly been from school, and so I'm not sure how many of you would have taken the classes where you would have been exposed to this. So I'm not sure how much this is going to be a review or how much it's going to be an introduction. But then again, in interest of time, I'm not going to be able to go through everything in detail. So first of all, binary logic is fairly simple, where you have two inputs, A and B, and typically you have different gates where you could use them to come out with values of true and false. The most common ones are things like AND and NAND, where AND requires both sides to be true, and everything else to be false. Whereas NAND is the reverse of that. And similarly, you have OR, where you only need one thing to be true, and if you have both the inputs to be false, it's false. And similarly, you have FOR, which is the reverse of that. And finally, you have XOR, or exclusive OR, which requires that if it's true that only if one or the other is true, and otherwise it's false. these are probably the most important gates. Plus, and in binary there are 2 to the 4th possibilities for these circuits, which gives us 16 different circuits. And it's actually fairly easy to make a list of these because there are only 16 of them. And some of them are trivial, such as everything is going to be true or everything is going to be false. But these are probably the most important ones. And actually, if you wanted to build circuits, this is probably the most important one right here. You could build a computer using just NAND gates. There's going to be lots of inefficiencies because you have to build. If you wanted an AND gate or an OR gate, you'd have to build them with a series of NAND gates. But it's theoretically possible just doing this, which is why the NAND to Tetris course starts out with only giving you a NAND gates and then having you build everything from there. So in terms of circuits, these things are typically written like this. So here's an AND gate, and similarly, there's you would draw a NAND gate with a little circle, indicating which is short for not. And basically, these gates it's relatively simple to create these gates using circuits. For example, if you could using a couple of NPN transistors. An AND gate would look something like this. And so the A and the B input, the A and the B input would control whether or not these transistors are on. If both of these are true, then the electricity would be able to go through the transistors and come out this way. And so this would be true. Now, if one of these is false, then basically that would mean you have 0 voltage. And so one of these would not be turned off, and the electricity wouldn't be able to go through, and so there wouldn't be any electricity coming out through here. And this is an AND gate right here, and a NAND gate would simply take the resistor and put it up here. And in this case, what would happen is if both of these are true, then the electricity would go straight through. But if either one of these are false, then this would be blocked, and the electricity would have to pass up through here. So an OR gate and similarly an OR gate has a circuit that looks something like this. And so basically, in this case, where these transistors are put one after another, in this case, the transistors are so basically these are in series. These transistors are in parallel. So all you need to do in order to get a true value is to turn one transistor on or the other. And actually, I deliberately did 2 transistors in this case, but you could. Technically, since each resistors, since each input can control, since you only need one switch, you could actually put several of these and feed it into a single transistor. I think there are certain advantages there are certain electrical advantages to having multiple transistors. And in later circuits, I'm going to show you that you're actually going to have multiple ones. Now, in the case, now there are some transistors that are actually, or there are some circuits that are difficult that are difficult to write as transistors, and XOR is one of those. So the exclusive OR actually requires you to a circuit that looks kind of like this. And so basically, if we have basically we take the we take the knot of the B and here and right, yeah. I think it's actually this is probably supposed to be over here. So basically, you take the knot of the A and the true A and then the false B, or the false B and the true A, and then you OR those together, and that gives you the result. But this is one of this circuit is actually really difficult to simplify, but it turns out to be really important for doing addition as well. And finally, you have NOT gates, which is and actually this is actually one of several urinary or unitary functions. And in the case of the NOT gate, it's actually fairly simple. You have a transistor. And a single transistor, and if you turn the transistor on, it allows the electricity to come through, and so this becomes 0. But if there isn't any electricity coming through, the electricity just goes through this way, and it becomes 1. And actually, the binary and binary, there are only four urinary functions. And they're actually very easy to write out. And so in this case, we have the NOT, which changes everything. And then there's the function I'd call amplify, which basically, if you were to have the output come out of here, then it'll just make the signal stronger, which in electrical circuits is sometimes necessary to make sure that is either to make sure the signal arrives in time, or by passing through a transistor and slowing it down a bit when you have a signal going through a series of gates, or it's sometimes necessary because after going through several gates, the signal could be weakening. And so basically true or false, and then you could either make everything true or everything false. And these are sometimes necessary to make sure that to ensure that that gates don't float to one value or another when you have a circuit where you might not be using an input. And so all four of these functions are technically used in binary. But strictly speaking, the NOT function is the most important one. And there's one other thing that should be pointed out is that if I were to replace these NPN transistors with PNP transistors, it basically flipped the circuit of and instead of using instead of being positive logic where everything is expected to be 6 volts or plus 6 volts, everything would become negative logic, and so we'd be using negative 6 volts for the circuits instead. So I'm going to move on to ternary logic, and I've already mentioned some of the possible reasons why we want to do ternary, but there are a couple of things that I haven't touched on yet, and I mentioned that we might not want to do ternary because of noise, but in addition to that, these circuits are going to be more complicated. But it's still an interesting option because notwithstanding the complication, it might actually turn out to be a more efficient logic. And it's also fun something that I've discovered is actually pretty fun to play with. And finally, one of the reasons why ternary logic might be interesting is because in quantum computers, apparently using ternary could reduce the complexity significantly. One example given where a binary circuit would require 109 gates in order to handle one qubit in a certain function, but the same gate using ternary gates actually ended up using only 9 logic gates. So it's not. When I learned that, I didn't really see the reason for that, but I'm thinking it's probably because in quantum mechanics you have a certain level of uncertainty, and ternary logic actually handles uncertainty in a natural manner. And so in ternary logic, instead of having just true and false, we have we also have an uncertain value, which you could call 0, or sometimes I'll use plus, minus, and 0 for the values. And because we have 3 inputs, we're going to have a lot more possibilities for the outputs. So I'm going to go over I'm only going to talk about and or, but and also XOR. Just to give a feel for what the ternary logic would look like. So just like we did with binary logic, we would say that 2 trues in a NAND would make a true, and 2 falses would make a false. However, when we have an uncertain value, then true, we don't know what's going to come out with in true when one value is true and the other is uncertain, because this could be true or this could be false, and so the result is going to be uncertain. But when we have false, however, so false and uncertain, we know that that's going to come out to be false. Because we only need one value in order for it to be false. And if we have 2 uncertains, it's going to come out to be uncertain. And similarly with an OR, if we have a true value, even if the other value is uncertain, it's going to be we know it's going to be true because we only need to know that one's going to be true. And similarly, if we have a false and uncertain, we don't really know what it's going to come out to be. So that will have to be uncertain. And again, if both of them are uncertain, they'll be uncertain. And finally, for exclusive OR, we can know that if both sides are true, then then it's true. But if we have an uncertain, it'll have to be uncertain. And if both are false, well, it'll have to be false. And everything would be uncertain. And basically, whereas binary functions are only 16 possibilities, in this case, because every single one of these slots has a possibility has 3 different possibilities, we have 3 to the 9th power of possibilities for functions, and so we have 19,683 different possibilities for functions. And so when I first started when I was at one point, when I was first beginning to understand the idea of these things, I decided to try to write out all these possible functions. But after getting to thinking that it's going to be 27 or 81 functions, but by the time I got to 81, I think it's actually probably just 27 functions. I realized I was nowhere near exhausting all the different possible functions. And when I actually sat down and really thought about how many functions there would be, the number astounded me. And so an interesting observation to point out is that I'm not sure how many of these functions could be simply realized in transistors. But to some extent, because there's a lot of wiggle room right here, there's a whole lot of possibilities for simplifications that might not be available in binary. And so and similarly, we could also do we have for a single value functions, we could have several. We actually, whereas in binary we only had 4 possibilities. In this case, we actually have 3 to the 3rd or 27 possibilities for unitary functions. The most obvious one is going to be the not function, which takes the true and false and swaps them. But because the uncertainty remains with the not function. In binary, you only need an AND or a NOT, or for that matter, a NAND in order to make all your circuits. In the case of ternary, having an AND and a NOT isn't sufficient, or not even having a NAND, because you don't have a way of converting the uncertainty to true or false. And so, in order to be able to generate everything in ternary logic, you have to have another function. And one possible function is something I call uncertainty to true, or you could have an uncertainty to false. And I'm also going to mention that a couple of other functions that may be useful, which one is a positive not, which would take a positive value and a positive or false value and make it into true, or a binary false not, or negative not, which takes anything that's not false and turns it to false, and then takes false and turns it to 0. And actually, I should point out that because ternary logic has so many functions, it's possible to find it's possible to include both binary logic or positive binary logic and negative binary logic in these functions. And now that I think about it, I haven't really explored this very much, but you could probably develop a logic based on uncertainty as well. and probably come up with other versions of binary logic that could fit in here as well. So a lot of times when we write ternary gates, there's a little triangle is added to indicate that a ternary, we're working with a ternary function. And so this is going to be ternary and. And the circuit, or at least the circuit I came up with looks something like this. So basically, theoretically, this circuit would take a true value, or two true values, and if both of them are true, then it should come out to be true, and if one of the values is false, then this part of the circuit right here would make sure that falses would come out. But if things are uncertain, then it'll turn off both the certain parts of the true and the false, and thus the output should be neither true or false, and so it'd be 0. And similarly, an OR circuit would look something like this. And so when I actually came up with the circuit, I realized something interesting about ternary about this, and that basically it actually took looking at the second circuit to realize what was happening. That this sort of portion right here is a positive OR circuit in binary, and so is. Whereas this circuit right here is a negative OR circuit, and similarly, this is a positive AND a positive AND circuit right here, and this right here is a negative AND. And so when I realized that that basically means that at least at the gates the basic gates that we typically would use for making a computer, the positive ternary logic and negative ternary logic are actually complements. And if you look at the truth table right here, you can see that here, if we turn everything from false to true, that the OR right here is the same thing as if we're using negative or false and, because false and false comes out to be false, whereas everything comes out to be true. And similarly, if we wanted to do false OR, this is actually this is the function where we could see that wherever we have a single false, it comes out to be false, and so basically we could use the same circuit for and OR, and this, or we could use this as an OR circuit and this as an AND circuit, depending on whether we wanted to use positive value for AND or negative value for, or a positive 6 for true or negative 6 for true. And I should add that these two circuits are two circuits that I don't have tested. And the reason being is because I tried to do a ternary knot. And basically, whenever I tried doing this particular circuit, one transistor or the other would end up getting too hot, and this is a circuit where I release the magic smoke. And I'm not entirely sure exactly what I'm doing wrong. And I do know that if I created either of these two gates separately, it would work like expected. And I think I even confirmed that I could do a ternary AND gate and have that work as expected. But I suspect that what's going on is that there's some sort of balance issue between the transistors, or I'm I'm doing something wrong with combining the output, and I don't really have enough circuit understanding to understand what I'm doing wrong. And so far, I've been able to talk to a couple of people about it. One is a physicist who couldn't tell me what I was doing wrong, because he mostly uses operational amplifiers in his work, which actually is more akin to using a continuous computer rather than a digital computer. And the other was an electrical engineer, or someone who got his degree in electrical engineering. And he couldn't tell me what I was doing wrong, because he tended to work mostly in digital circuits, which are typically binary. And there are other types of circuits as well that I sort of have written out, but I'm not really satisfied as to one way or the other as to whether or not they'll work. And so there are a lot of circuits I would like to design and try to get a better understanding of it. And actually, there's one other thing I wanted to talk about before I moved on, and that is just to compare the powers of two between binary and ternary. So if we just to get a feel for what happens with the powers, we're probably pretty familiar with how binary powers tend to how fast they tend to raise. Now, ternary, on the other hand, Ternary, on the other hand, moves or grows at a bit faster of a rate. So, for example, if we looked at Intel's first microprocessor, which is 4 bits, we could see that that gives us 16 possible instructions. Whereas with ternary, if we do if we were to look at 3 trits, we could see that we have 27 possible. We'd have 27 possibilities. And similarly, if we go to and I chose 3-trit just because 3 seems to be a natural number to use with ternary. But in some ways, the number of bits or trits we use is actually arbitrary, and I'll point that out in a little bit. But if we wanted to do, if we wanted to compare 8-bit with 6-trit, we see that's 256 versus 729, and although I haven't written down 16 or the next level, we have 16-bit, which gives us about 65K values. A similar a 12-trit computer would give us about 530,000 different values, and we could continue to make comparisons like that. So basically, we could see that with ternary, we actually have for a single value, we actually have more potential for growth and for that matter, a greater potential for keeping things smaller. Now I'm going to I'm going to mention memory a little bit, but in interest of time, I'm not going to be able to talk about everything I wanted to talk about. But the most common way of doing memory in binary is to use 2 different types of is to start with 2 things called latches. And this is called a NAND, not RS latch. And then we also have a NOR. A NOR RS latch. And the idea is if we the R and the S stands for set and reset. So if we wanted to set this to a value of 1, we would send this. We would send S to high and then R to I think both. Yeah. Actually, I forgot to include the truth table for this, but if we wanted to send this set this, for example, we would send. If we send R to 0, or not R to 0, if we send this to 1 and set this to 0, then our Q would become 1, and our not Q would become 0. And similarly, if we reverse that, then we'd end up getting then we'd get 0 and 1. And finally, if we set both of these to 0, Q would be whatever we just set it to, and not Q would be the opposite of what we just set it to. And so this gives us a very basic form of memory. And but it has a disadvantage where if we put both of these to 1, we receive a contradiction and we have no idea what becomes of this. And so there are certain techniques, adding gates and enables and things like that, that makes the circuit more complicated. but also makes it a more reliable and to make sure that we don't get 0 and 1. Now it turns out that this is that probably either of these would be sufficient for memory and ternary computing as well. But it actually took me a long time to figure that out and actually become comfortable that it would work. And part of the reason why that is because in binary, we have the simple table. We have a simple table that looks like this, where we just have 4 values we have to figure out what's going on in here. With ternary, though, we have 9 different values and to try to figure out what's going on. And at one point, I actually concluded that this would be impossible to work. But then I realized that remembered the duality that I discovered earlier where the negative logic and the positive logic are basically duals of each other. And it occurred to me that a negative ternary latch would just be giving would be this kind of circuit right here. And since this circuit would work in binary and this circuit works in binary for memory, that this as a ternary circuit would work as well. Now there's one other form of memory I quickly want to mention, and that is dynamic RAM. In binary, there's a there is a relatively simple way to store a value, which is to have a transistor and a capacitor. And when the capacitor is charged, it's considered set or whether it's set to 1, and if it's empty, it's set to 0. In order for this to work, you have to have a big complicated structure, which this is where you're constantly reading the capacitor to keep it refreshed, since the charge keeps on going to 0. Which is why when you turn off the computer, this disappears instantly. But the reason why I want to bring it up is because it's my understanding that capacitors could hold a positive charge or a negative charge, depending on what charge you give it. So it may be possible to create some sort of circuit where this capacitor is where the single capacitor is can work as a ternary memory module as well as a binary one, and so so I haven't been able to figure out how that might work. But if that works, then it'd be really intriguing to be able to create a ternary version with just a single capacitor. So there's another thing I wanted to add was that there are actually 3 different types of memory. These are called flip-flops, and because they're really fast and they don't really require and they work all on their own. They typically are used in the important parts of the computer, like registers and code pointers and so forth. And then we have this thing. We also have another thing called static RAM, which in binary is made out of two NOT gates, which I haven't been able to figure out how it might be converted to ternary yet. But that's typically used. That's not as fast as flip-flops, but it doesn't use as many transistors either. So it's typically used in cache. And then there's this version, which is really simple, but it's also rather slow, and it also requires a big, huge huge infrastructure in order for it to work. And so this is typically used for system memory, and uh, um, and this is what you typically would install when you're installing a memory card into a computer. So the next thing I wanted to talk about was addition was addition. And basically, it turns out that addition is relatively simple. You use an exclusive OR to do the sum. And then add to do a carry. And this circuit right here is called a half adder. Because all it can only handle 2 bits. If you wanted to be able to handle a carry from a previous addition, you'd have to add another half adder to make a full adder. And and when you put these together, actually, we could basically put these together for as long a string as we want to be able to add as many any 2 lengths of binary strings together to get a sum and a carry. Now, this is called a ripple adder, and it's probably the simplest of adders, but it also has a disadvantage in that and that it takes a while for a single sum to basically ripple all the way through in order to get the final answer. So this has been the subject of a lot of optimization. Both the original circuit, which it's my understanding there are circuits that get this all the way down to just 8 transistors, which is a lot more complicated than the typical exclusive OR circuit I'd drawn earlier. And there's also optimizations for the carry, such as something called a coax stone adder, or a carry look-ahead adder, or a carry save adder. And they all use various techniques to try to parallelize and otherwise help to speed up the addition process. And the adder is also important because it allows it makes it possible to do calculations to figure out where you might want to jump ahead and code, or where you might want to, or how to increment the code pointer or other things like that. So for that reason, this is something I've also tried to optimize as a ternary circuit. And so far I haven't been successful, but a ternary But the ternary circuit I've come up with so far looks something like this. And so basically this actually introduces a couple of gates. One is that this is called a decrement. That this is basically is identity, and this is this is plus. So essentially, what's going on in these particular gates is it takes the decrement takes us backwards in a circle, whereas increment would take us forward. So for example, if we take a 0 and add 1 to it, we get here. And if we add 1 to this, we get to here. Similarly, we'd go backwards with here. And this is a circuit that a particular circuit that is kind of complex. Oh yeah, and also this is something called consensus, where it's something that's only that's true if both values are true, or false if both values are false. Otherwise, it's uncertain. And the idea is and this circuit actually uses something called a balanced ternary, which is something that is one of the things that I consider one of the most interesting things about ternary, and that is if we have if we have binary, we every time we add one to a circuit or a value, if it's 0, it's obviously 0. But if it's 1, we set it to 0, and if we try adding 1 to 0, it becomes 1. But if we add 1 to 1, that becomes 0, and it carries over to 1. Well, in basic ternary, we have the same idea where except for we have 2 digits, and so 2 plus 1 is 0. It carries over to 3. But balanced ternary, and basically our digits are 0 and 1, and here our digits are 0, 1, and 2. Now in balanced ternary, we do something a little different. Instead of having our digits to be 0, 1, and 2, we actually have our digits to be 0, 1, and -1, which I typically write as positive and negative. And so in this case, we have 0, then 1 is positive 1, and 2 is going to be 3 minus 1, and 4 is going to be 3, 0, and 5 is going to be 3. Wait. 3 is going to be 3, 0, and 4 is going to be 3, 1. And 5 is going to be 9 minus 3 minus 1. And so one of the interesting effects of balanced ternary is that if we wanted, this actually gives us a negative representation for free. Because if we took all these signs here and just swapped them, it would be the same number, only it would be negative. So for example, this would be -1. This would be -3 plus 1, so that would be -2. And so we could and so as a result, there's a natural representation of positive and negatives that would fit in that would fit naturally in the same space. And so this is naturally another thing I wanted to mention is that because this this is actually a bit more complicated than the binary equivalent. But one of the disadvantages I have right here is that in trying to figure out how much simplified the circuit can be made, actually I have a bit of a disadvantage because people have been working on simplifying and optimizing binary functions for decades in an effort to get computers as efficient as possible. So it's a bit of a challenge to try to figure out how simplified a ternary circuit could be made when I'm still in the process of trying to figure out what they're looking at in the first place. Now, there's one other important function that's useful, that's important in ternary, which when you're working with binary computers, you don't even think of it as a function because it's relatively easy to produce, and that's called a decoder. And basically. What happened was I was looking at various different ternary circuits, and one of the circuits I had mentioned just now is something called consensus. And I was trying to figure out what this circuit for consensus would look like, and for that matter, I've been running into other ternary gates that were interesting and potentially useful in helping the computer to be designed. So I got to a point where I wanted to create a truth table so that if I could create a circuit and I could just plug it in, and the LEDs would show me true, false, and uncertainty, and then I could see if things are what I would expect it to be. And so my idea was to create two signals, an A signal that would go positive, and then alternate from positive to negative, a B signal that would do the same thing, but would do it three times as fast. And then I'd plug it into a circuit that would look something like this. Basically, I'd put it into something called a decoder, which would translate the A signal to, and it'd be true it would come out to be true if the first one would come out to be true if A is true. Otherwise, 0 would be true, and then false would be true, and it would be false otherwise. And then I would take these outputs. And create a create a truth table that would look something like this, where the gates true inputs would come out in this corner, then true and false, or false and true, and so on and so forth. And so and these circles are supposed to be two-way LEDs, red and green, and then they red and green together for insertion to make yellow. And so what I did was I tied a bunch of these LEDs to AND gates, and then the true gates would go up, over here and feed into here. And the insertion gates would feed into here. And similarly, for the B value, it would come through here and go to be the second input. And basically, when I'm not going. And then I put the gate right here, and that would go into to the third part, into all of these other AND gates, so that if this is true and these two came out to be true, this would come on as true, and so on and so forth for each of the lights. And basically, when I got to this point, I realized that I could take any input and I could decode it and come up with anything I wanted to do. So I'm running out of time, and so I'm not going to be able to go over instructions and so and everything I wanted to do. But I will try to give a quick example. For example, if I wanted an instruction, if I wanted to load up an instruction, I'd load it up into, in this case, I was working to create a three-trit computer, so it would have three possible values for the instruction, and then I'd have these other bits of information for the instruction to work on. So in memory, the single instruction would take up 9 trits in memory, and I would have to admit that this is actually I was kind of inspired by the RISC architecture where every instruction is the same length. But basically, what would happen is what I would do is I'd take an instruction. And then I would send all these things to decoders. And if I wanted to decode, say 0, negative, and plus was my add. My add function, it would take the 0. These would be fed into an AND, which would enable enable the add function, and then I would use decoders to feed the registers the registers into AND, which would then take that and send the output into the result register, depending on how I wanted to design the computer. And so basically, between using a lot of AND gates and a lot of decoders, I could do whatever I would like to do. I could access different blocks of memory. I could create using flip-flops. I could create registers that would point to that would allow me to set libraries and books and pages for memory. But even though I'd have to confess that in my computer design I was getting a little ambitious for something that's supposed to be rather simple. But basically, once you have an understanding of how these things work, it can be relatively simple to try to figure out how you're going to access different parts of the system, and then execute an instruction, and then move to the next instruction. So in conclusion, I'd say that what surprises me is that anyone could really do this if they put their mind to it, which I guess is also the point of from the NAND to Tetris book that I pointed out before. My another thing that conclusion I have so far is that I'm still undecided on ternary versus binary for efficiency, in part because I'm still struggling trying to understand how the circuits will work and what optimizations are available. But I've also decided definitely that designing circuits can be challenging if you don't have an electrical engineering degree. And given the brief conversation with someone who does have an electrical engineering degree, I suspect that under certain conditions they're probably challenging even if you do have one. And I've also discovered something. Another interesting thing is that ternary is a lot more fascinating than binary. There's a lot more richness to it, in part because you could express uncertainty when you in certain ways, and in a way that binary is kind of hard to do so. I kind of explored quad logic as well, and that allows the possibility to express contradiction as well as uncertainty. But there are a couple of reasons why I didn't quite find that as fascinating as ternary. One is being that you could easily get to quad-based logic just by having two binary gates put together. The other being that when you have four values in your logic, the circuits and the logic get a lot more complicated really quickly. The fourth thing that I've come to realize is that if I could actually get to the point where I could build this computer probably out of at least the one built out of transistors, I think it would be really neat to be able to call that computer a Ternavac, kind of the same way that the Univac was built with using tubes back in the 50s and 60s. I wanted to mention a couple of resources in particular, and there are a lot of resources that over time I've lost track of, but these two in particular have stood out enough that I've been able to find them. One is www.nand2tetris.org, and this also has a book that accompanies it that goes through the process of designing a computer, starting with gates and going all the way up to the operating system. The other resource is on ternary logic. And that is at homepage.cs.uiowa.edu/tilde-jones/ternary/logic.shtml. And this page actually goes through a lot of the possible logic gates that are useful in doing ternary computing. And it's actually a page I discovered while I was rather deep into trying to design a ternary computer. And I found I found that the summaries of different types of gates rather useful. And actually, if you go up one level just to tilde-jones/ternary, there's also a lot of interesting resources about ternary computing in general, as well as some discussion about whether or not balanced ternary is more efficient than the binary equivalent. And it kind of leans towards no, it's not. But I'm still not quite convinced, mostly because we've done a lot of work to optimize a binary addition, but there isn't nearly as much work having been done to optimize ternary. And so I think that I'd like to see more optimal versions of ternary circuits before I could say one way or the other whether or not it's more efficient. So that's pretty much all I have for today. Are there any questions?
Alpheus, a cool presentation here.
Right, thanks.
All the logic's very interesting. Of course, when you do something like this, you've got to look at what's available to me, what can I do tool-wise, etc. Yeah. But probably the good thing to do is to know how this would be beneficial, and then what are the limitations. Then you start looking at what technologies can help you with the limitations. You mentioned one about, I think you were alluding to the fact that binary has been around a while, so you've got all these Boolean equations, and so are you going to invent ternary equations or whatever like that? You're also playing with, it's been a long time since I've seen a PNP transistor. Most of the world is CMOS, and it'd be interesting to redo the whole thing with CMOS. So you drop a bunch, of course, you're doing breadboarding, right?
Yeah, I'm doing breadboarding right now.
Right, I don't know, the CMOS lends itself very well to breadboarding.
Well, there are some things issues I have with that. That I'm actually interested in trying to do the same thing with field effect transistors, and just like the fact that binary basically this is the logic I've been working with is resistor transistor logic, and I chose that because it's simpler than some of the other types of logic. And I'm interested in trying to use FETs as well because, in part because field effect transistors you have something like 4 different types of FETs. Like you have N-channel and P-channel, which is the same thing as NPN versus PNP. But you also have complementaries where you have always on versus always off. And so with CMOS, you have 4 different types of transistors to play with, and I think that would be interesting to see how that would work out in ternary logic. And there's another transistor that I've only seen rumors about and trying to figure out how the circuits are supposed to work. One is that there's apparently a bipolar transistor that's somehow balanced so that it could be either NPN or PNP depending on the circumstances. If I could find actual solid information on how that's supposed to work, it's at this point to me it's just a rumor, so I don't know what kind of role it could play, but I kind of have a suspicion that might have an interesting role in ternary logic as well.
Talking about some other ones.
Okay. Are there any other questions?
Have you made any attempts to simulate this?
I haven't yet, and I actually suspect that if I could simulate it, it would allow me to take care of things like factor out the imbalances of between transistors and resistors and so forth.
And that's what I'm thinking. You might be able to iterate faster or kind of simulate something before you build it.
Yeah.
And burn all your transistors, but also let's see. It'd be interesting. You're a programmer, and so you could program the basic building blocks, and you can take those and you can create your computer in your arithmetic units and experiment with optimization. And so have you made any attempt to do that?
I haven't made any attempt to do that either, but it's something that has crossed my mind.
Something I could note too, actually, as you, in computer arithmetic, when we were optimizing it, we actually take it to different numbering systems, and it all goes back to the digital as it's implemented, but that's something you might find interesting, using different bases. And also a quick question with, so you represent, like, 0 as uncertainty. You're doing your logic. And you also talked about using, I guess, representing like a redundant number system, or doing like a -1 and 0 positive. And so, I guess from what you're experimenting with your truth tables change, representing those as different, where it doesn't mean uncertainty, where you are using the numbering system. I don't really know how to word this, but.
Okay. You mean for addition, or for arithmetic?
I guess ultimately you're kind of thinking this as voltages, right?
Yeah, I'm kind of thinking as voltages, and in that sense, it's my understanding that voltages can be rather arbitrary. Like you could set up circuits so it's 0, then 1/2 on full voltage, for example, and for that matter. You could set choosing true, false, or 0 for each of the different levels can be arbitrary as well. But I kind of I haven't really tried experimenting with variations on different types of how I might rearrange the voltages, but. I could imagine that in certain cases it might simplify things, but in other ways it could make it more complicated.
And then, so with 0 doesn't have to represent uncertainty in the case of the logic you have, right?
Yeah. In terms of I'm not quite sure what else you'd use 0 to represent, but for at least for AND and OR gates, the 0 would typically represent uncertainty, but when you get into to arithmetic, the 0 would you move into from doing it ands and ors to representing them as numbers, and I think that's one of the reasons why the circuit I drew is more complicated. Because it's a lot easier to go from positive to 0 or negative to 0 than it is to switch negative to positive. And the truth table for sum actually requires you to if you go back to the, let's see.
Yeah, do your resources use the same symbols that you use in your?
Yeah, they do. Let's see.
Very interesting, by the way. I appreciate your lecture.
All right, thanks. Like if you, so basically, there are a couple of ways you could represent numbers, and that one is, and this is using the typical unsigned. So basically, you have 2 zeros would go to 0, and 0 and 1 would go to 1. But then you have the 1 and 2, which would go to 0 with carry, and then 1 and 1, which would go to 2. And so if you're representing 1 with 1 is positive and 2 is negative, you have this case where where 1 and 1 goes, where 2 positives go to a negative. And dealing with that case, and for that matter, trying to deal with the carry, where you have a positive and a negative goes to a positive. Whereas in other cases, if you have basically it can be tricky to figure out how to make that kind of transition.
And a 2 plus 2 would give you a double carry.
Yeah. Now, if you do 2 plus 2, then that would give us
Oh yeah, a carry.
yeah, a carry into 1. So that you have to do 2 positives. And even if you do balanced ternary, you have similar issues. So basically, with balanced ternary, if you have 2 negatives, you get a plus and a negative carry. Whereas if you do 2 positives, you do you get plus and or you get negative with a plus carry. So you have to figure out how to get these 2 cases to completely reverse voltage. Whereas here you somehow add the voltages and get 0, which to me it should be fairly straightforward. But it's trying to achieve this in the ANDs and OR gates, or even the NOT gate that's resulting in burned transistors. And actually, in some ways, the balanced ternary might potentially be a little bit easier to deal with when it comes to doing the carry. That's where the consensus comes from, where if it's 2 positives, you get a positive, or 2 negatives, you get a negative, and everything else is 0. Whereas in this case, when you're trying to do unsigned, everything the carry is always going to be positive, and you have 3 different cases where it's yeah, you have 3 different cases where it's going to be positive, and basically it's you have this case right here where 1 and 2 or 2 and 1 give you the carry, or you have this case where the 2 and 2 give you carry, and everything else is pretty much is 0. So it's kind of difficult to figure out how to get carry from there. Particularly if you have a 0 and a 1, like it just really occurred to me that perhaps you could it might not be a little bit simpler, but then I just realized that you have the thing that makes it tricky is if you have you have to go to positive when you have plus and minus, but or 2 minuses, but otherwise it has to go to 0. And so you can't just say, well, if you have a minus, then you go to and then you switch it to positive, because you also have to take into account that if it's 0, that it's not supposed to do that. Are there any other questions? Okay.
Thank you.
All right, thanks.